For our last new topic of the unit, I want to distinguish between two types of collisions. Now, what I'm about to say doesn't change anything that I've said earlier in this unit. When we've analyzed collisions using conservation of momentum in one dimension or two dimensions, we'll continue to do that, and we'll continue to do that in the same way. But we can now classify these collisions in a different way. We're going to classify these collisions as either being elastic, or inelastic. An elastic collision is a collision in which, of course, momentum is conserved. Momentum is always conserved in a collision as long as we have an isolated system, as long as there's no external forces. But in the elastic collision, kinetic energy is also conserved. So you don't gain or lose momentum, you don't gain or lose kinetic energy. Versus an inelastic collision where you don't gain or lose momentum because, again, in an isolated system, momentum is always conserved, but you do lose kinetic energy. Kinetic energy is not conserved. Kinetic energy is lost. It'll never be gained, by the way. Okay, it'll always be either stay the same, conserved, or it'll be lost. Now, realistically, when do we see a collision in which kinetic energy is conserved, which kinetic energy is not conserved? Let me give you an example of a collision that is almost elastic. Two billiard balls hit each other, bounce off of each other. That's almost an elastic collision. It's not perfect, but it's real close to elastic. Let me give you an example of a situation that's an inelastic collision. Two cars hit each other and they entangle. Let me give you another elastic collision, or something that's close to elastic. Two curling rocks bounce off of each other. Let me give you another example of an inelastic collision. A basketball bounces off the floor. Does anybody want to take a stab at when we would typically have an elastic collision and when we would typically have an inelastic collision? Okay, there's a good way to help distinguish. If two objects stick together, it must be inelastic. Kinetic energy will be lost every single time two objects stick together. But if two objects bounce apart, it could still be inelastic, or it could be elastic. Okay, so if you see a collision in which two objects bounce apart, you don't know whether it's elastic or inelastic. It could be either one. If you see a collision where they stick together, you know it's got to be inelastic. Nick?
Would it be like elastic is like X?
Okay, good guess, but no. Has nothing to do with one dimension or two dimensions or X or Y. Okay, you can get elastic in one dimension, two dimensions, three dimensions for that matter. You can get inelastic, same deal. Remember the examples of elastic. The pool balls hitting each other, and the curling rocks hitting each other. The inelastic were the cars hitting each other, and the basketball hitting the floor. What's the difference between pool balls, curling rocks, cars, basketball? 1 second here. Yep. Not the mass. Yep. Nope. Friction's an external force, so we want to stay away from that, right? It makes it not an isolated system. Here's the deal. When two objects that are really, really hard collide, it tends to have a better chance of being elastic. If they're soft and can deform, it's going to be inelastic. Here's why. You guys remember from Science 10, whenever you have an energy conversion, you always lose a little bit. The second law of thermodynamics. Do you remember that? Vaguely, at least. Whenever you convert energy, you lose a little bit. If a basketball hits the floor, what happens? Kinetic energy is converted to elastic potential energy as the ball compresses, and then it's converted back to kinetic energy as the ball gets fired back up into the air, right? There's energy conversions taking place. We lose a little bit, so therefore we can't possibly have as much kinetic energy afterwards as we had before. Same deal with the cars. When they compress, we're converting energy from kinetic to elastic potential. We lose a little bit in that transformation. When two billiard balls hit each other, how much do they squish? Not very much, right? So there's not very much of an energy conversion taking place. Therefore, it's going to be close to elastic. The only time we have truly elastic is when we have subatomic particles colliding. Why? Because they can't compress at all, period. So there can't be any energy conversion that's taking place there. Make sense? Okay, we'll pick that up tomorrow.